Now this reaction, when you involve a catalyst, contains, in this next slide here, it contains hundreds of reactions. And each of these reactions has different parameters which control the rate. And basically we solve for these parameters using theory, density functional theory, transition state theory. And basically what those come down to is equations of interacting particles, equations that you might see in your physics class. Wave equation of electrons or harmonic oscillators, spring constants, things like that. Just these regular physics equations. Put them into, we can simulate the way two molecules will interact, two atoms will interact, how atoms interact with the surface. And we can come up with rate constants for all of these chemical reactions. Basically, that threshold energy I was talking about is what we're trying to calculate. So basically, you can see when we put this model to use, we can predict experimental data pretty well. So that gives us a good idea that we actually know what's going on the surface using just computers. Computers and equations. So looking specifically at ethylene glycol. So this is an image from one of those simulations. This is ethylene glycol, what it looks like when it's close to a metal surface. You can see the oxygens like to interact with the metal. The carbons kind of point upwards. So here's a sketch of it here. But basically what we can do is a reaction path analysis. And essentially what this is starting from the reactant, we can calculate the rates of each of those individual reactions and figure out step by step how we get to the product, which, carbon monoxide and these C1 species. Basically, we've broken down ethylene glycol to simpler molecules, and then we'll do that again to get to hydrogen and carbon monoxide. But basically, something that we find when we look at these simulations is that the atomic binding energies, or the strength of the atoms binding to the surface, are good descriptors for active catalysts. So the word descriptor, does anyone know what that is? Okay, so a descriptor is basically something that will tell you how good of a catalyst it is. Something simple. So basically we're looking for things that we don't have to really go into depth to find to give us feedback of how good a catalyst is. So if I can think of a metaphor real quick. If you guys like, I don't know, basketball, one descriptor for a great basketball player might be that he's tall. So if you see somebody that's really tall, maybe he's good at basketball, maybe not. But if you start to put all these descriptors together, he's tall, he's fast, he's good at sports, then yeah, he'll probably be pretty good at basketball. So the descriptors we find for these metals being active have to do with atomic binding energies. Basically, how strong does oxygen bind to the surface, how strong does carbon bind to the surface, and how strong does hydrogen bind to the surface. So using some semi-empirical methods, what we can go ahead and do is we can try to optimize our catalyst. So basically, this is a contour plot. One axis you have carbon binding energy, one axis you have oxygen binding energy. And what we see is that the darker red it gets, the more active the catalyst. So here's kind of a side view. You can see that there's kind of like a hill here. So we want to have a catalyst that is at the top of this hill. So experimentally, we go ahead and we can test some of the catalysts that we predict to be active. So platinum's always active. So we start there and we looked at nickel because it's cheaper than platinum and maybe it's more active. It turns out it's about the same. And then we look at some bimetallic catalysts, basically mixing metals together, bimetallic, two metals.
So, Mike, do you make alloys at different concentrations?
Right.
How
yes.
do you prepare them? Those.
Yeah. So if you see the way I've written these, you have platinum, nickel, platinum, and you have nickel, platinum, platinum. Now, basically, what these are is I should have brought a picture of this, but it's if you think about layers of platinum atoms of your platinum metal, nickel, platinum. Or platinum, nickel, platinum is one layer of platinum, one layer of nickel, and then one layer of platinum. So you've got nickel sandwiched in between 2 layers of platinum. Now this other one, which is the most active one we found, this nickel platinum platinum is essentially platinum, and then we deposit nickel onto the surface of platinum. So we do this in an ultra-high vacuum chamber, basically, which means it's very low pressure. There's platinum surface, and we kind of sputter nickel onto it at a certain temperature, and it will spread out onto the surface, and we can create this metal, this catalyst that we want. So it's nickel on top of platinum.
Mike, for the students to get an idea, what's the average thickness of these layers that you like to be? What's the range?
Oh, this nickel is 1 atom. That's how thick it is. So, I mean, 2 angstroms, 2 to 3 angstroms, which an angstrom is a unit of length that's 10 to the negative 10th meters. So, I mean, tiny. I mean, 1 atom. I mean, microscopic thickness. You can't see it.
How about the other one? Platinum, nickel, platinum.
Right. Again, this is 1 layer of nickel, 1 atomic layer of nickel under platinum. Basically, you make these the same way.
How thick is the platinum?
The platinum.
Same thickness?
No, the platinum is several layers thick, maybe a nanometer or so, which is about on the order of 20 layers thick. I mean, basically, because if you remember, these are expensive metals, so we want to use as little as possible.
And
So
the highest surface area.
basically, what we do is to increase the surface area, spread it out as thin as possible over, because really we're only using the top layer. Anything that's not on the top layer is pretty much being wasted. So the thinner we can make these, the better off it is for our bottom line. If we can make one 10 layers thick versus 20 layers thick, we're saving half our money on catalyst expense. We make this nickel platinum platinum, and then if you heat it up to a certain temperature, the nickel goes under the top layer. It's a complicated process, but we know how to make it, and we've characterized it, so we know what we have here. Some of our colleagues, Professor Chen and Orst, one of his former students, looked at these systems for ethylene glycol and confirmed that these, our model, which is based off nothing but equations and computer simulations and interactions between molecules that we calculate from physics, is able to predict what happens in the real world. So essentially what we've done is we've putting this type of a simulation in the computer takes, it takes a long time to set the model up, but when you push the button and have it run, it takes hours. If we wanted to actually look at this entire range experimentally, this would take decades. To find metals that have oxygen and carbon binding energies over here and all over, it would take years and years. So essentially, computational chemistry gives us an idea of where on this surface to search to find these active materials. As it says in this last point, using these computational resources, we can screen for catalysts and use that for catalyst design, so that we're not randomly searching. Basically, these are theory-guided experiments. Right? We use theory, equations, physics, chemistry, to pinpoint exactly what we want to look for in the lab. Because everything we do in the lab takes a long time. It's hard. It's hard to set up. It's expensive. So combining what you learn in a textbook to what you learn in the lab is really a useful way to go about doing research.
What's the correlation factor between the computational analysis and the experimental data? Is it 70, 80%, 90 or 20% correlation? Do you guys have any idea?
What do you?
The predictability of the model here.
Right. So the predictability is